All right, today we're going to talk about one of the most important, most influential papers in the history of AI. It's called Deep Residual Learning for Image Recognition. Now, it came out back in 2015, and it's really the story of a brilliant and almost deceptively simple idea that just smashed through a huge roadblock in deep learning.
And it all really comes down to this one question. How did a single, simple shortcut manage to solve a problem that had the entire field of AI totally stumped? How did it let models get deeper and way smarter than anyone even thought was possible? Well, let's get into it.
So, to set the scene, our story starts right in the middle of what you could call a deep learning arms race. Back then, the thinking in the field, the prevailing wisdom, was pretty straightforward.
Everybody believed that deeper networks were better networks. The logic was pretty sound, right? More layers, more depth, means the network can learn more complex, more intricate features from the data. So if you wanted a more powerful model, you just stacked on more layers. And you know what? For a while, it totally worked. People were building networks that were 20, even 30 layers deep. But as they tried to push even further, they hit a wall. A really frustrating problem where the training signal, the gradient, just got weaker and weaker as it traveled back through all those layers, making it almost impossible for the network to actually learn anything. And this is where things got really weird. As researchers tried to build even deeper models, they ran into this bizarre, totally counterintuitive problem that just seemed to defy all logic.
The paper's experiments showed something that was frankly shocking. A 56-layer network had a higher training error than a much shallower 20-layer network. Now, think about that for a second. The deeper, supposedly more powerful model was doing worse on the very data it was being trained on. This wasn't a case of it failing to generalize to new data. It was a fundamental failure to even learn in the first place.
And the authors, they made this crystal clear. They said, look, this isn't the usual suspect. This isn't overfitting, where a model just kind of memorizes the training data. No, this was something much deeper, much more fundamental. Adding more layers was actually actively making the model worse.
So this was the big mystery that had the whole field scratching their heads. In theory, a deeper network should perform at least as well as a shallower one. I mean, in the worst-case scenario, those extra layers could just learn to do nothing, right? They could act as an identity function, just passing the information through unchanged. But for some reason, the networks were really struggling to learn even that simple task.
The breakthrough, the big revelation, came from a really brilliant change in perspective. Instead of forcing these layers to learn some super complex function from scratch, the researchers asked, what if you just asked them to learn the change, the little correction from the layer before it?
And this is the core idea of residual learning. The best way to think about it is like you're an artist. It's incredibly hard to draw a perfect portrait starting from a totally blank canvas, but it's much, much easier to take a pretty good sketch and just add the small corrections, the little tweaks needed to make it perfect. The network was now only being asked to learn those small corrections. That's the residual.
Okay, so here's how it actually works. This is the residual block. Your input, let's call it x, goes into a couple of processing layers. Those layers learn a function, which we'll call f of x. But, and this is the genius part, the original input x also goes down a separate path, a shortcut connection, that completely bypasses those layers. Then at the end, you just add the two paths back together. The final output is the original input x plus the small modification the layers learned, f of x. What this means is that if the best thing for the network to do is nothing, that identity function we talked about, it's super easy. The layers just learn to make f of x equal to 0. The shortcut makes the hard problem trivial.
And the result of this elegant idea? Well, it didn't just solve the degradation problem, it completely shattered the barriers that were holding back deep networks.
The numbers just tell the story perfectly. You take two 34-layer networks and compare them head-to-head. The plain version, the one without shortcuts, it had a pretty high error rate. But the residual network, the ResNet, at the exact same depth, performed significantly better. Just like that, the degradation problem was solved. Deeper was finally better again.
So, with this huge fundamental roadblock just completely demolished, the floodgates flew open. The question was no longer if we can go deeper. It was just how deep can we possibly go?
The answer was a staggering 152 layers. Now, this wasn't just a small incremental step. This was a massive leap forward, creating a network that was 8 times deeper than the previous state-of-the-art models like VGG.
And with that unbelievable depth came unbelievable performance. An ensemble of these new ResNet models hit a record-shattering 3.57% error rate on the super challenging ImageNet benchmark. It was a new world record.
It was a total clean sweep.
In 2015, Resonant didn't just win, it absolutely dominated. It took first place in every single major computer vision competition: classification, detection, localization, segmentation, all of it. This was a true paradigm shift.
So, why are we still talking about this paper all these years later? Because its impact went so much further than just one model or one set of competitions.
What ResNet really did was introduce a foundational principle. That shortcut connection became a standard, essential tool in the deep learning toolkit. It's a fundamental building block that's used in countless modern architectures today. It's what enables the ultra-deep networks that power so much of the AI you interact with every single day. And maybe the biggest takeaway is the lesson it taught the entire field. Sometimes, the best way to solve a really hard problem is to reframe it, to make it easier for the model to learn in the first place.
And that, of course, leaves us with a really fascinating question for the future. ResNet's simple shortcut unlocked a whole new era of deep learning just by making the problem easier to solve. So what's the next elegant, simple shortcut that's going to come along and redefine AI all over again?